Hi, this is Aries Itten, and this workshop is Deploying and Managing Models using SAS Viya. We'll be learning how to use some of the tools in SAS Viya to make it easier and more efficient to keep track of the models that you build and where and how you're going to deploy them. When we build models, we like to start by looking at the analytical lifecycle to motivate our work. We start with data. We've collected some sort of operational data from our business, or we've collected data through some sort of data collection program. We need to prepare this data for modeling, put it into rows and columns, figure out useful inputs for building predictive models. In the discovery stage, we're actually going to learn things about this data. So we might look at some of the inputs, understand the distributions, look at relationships between inputs and targets. Once we've learned a little bit about the data, then we'll go ahead and build the models. That's really still part of the discovery phase. This is building predictive models for business value. It could be something like trying to predict who's going to default on a loan so we can decide who to prioritize assigning loans to. After we've done some discovery and built our models, we go to deployment. This is actually using the models to generate business value. So I mentioned an example would be trying to figure out who's going to default on the loan. Deploying the model would be actually offering loans to the people we think are unlikely to default on loans, or rejecting people for loans who we think are likely to default. The deployment stage is actually using the model to drive your business value. In this workshop, we'll be mostly focusing on the deployment phase of the analytical lifecycle, but it is a cycle. So once we deploy our models, we collect more data about how that deployment went. When we've decided who to give a loan to or not, we can afterwards, 9 months later or a year later, determine whether or not people are paying back their loan on time to then build another machine learning model based on previous data from the previously deployed machine learning model. So the idea of this cycle is that every time we deploy our models, we're going to generate new data for further models in the future. And we'll see in Model Manager, which is a software we'll be using today, there are tools that are going to make it easier to keep track of how your models are either developing or potentially degrading over time. In this demonstration, we'll be registering some SAS and open source models from pipelines and from some code. So we'll see some demonstrations using Model Studio and then moving into Model Manager. We'll start by going to SAS Drive, which is the SAS Viya landing homepage basically. I'll sign in with my username and password. We just have a student test account. I am not an administrator, so I will not sign in as administrator. We're just going to use this as a user, basically an analyst who's building predictive models. We land on this SAS Drive homepage. We're actually going to go to Build Models. So in the top left, I'll click the Show Applications menu, and I'll select Build Models to take me to Model Studio. So this is the SAS Viya server / Model Studio. Model Studio is organized in projects, so we will start by creating a new project. We'll name our project Model Manager Workshop, because this workshop is on Model Manager. We'll start with a blank template, and we'll do a data mining and machine learning project. We'll browse for some data, and we'll upload a local data set up to the server. So I'm going to click Import, choose Data menu, Local Files. I'll select a local file. I've got a little data folder in a course folder. I'll select this hmeq.csv. This is a comma-separated value file. I'm going to upload this into the public library, and I'll just click Import Item. Oh, the table already exists. I forgot to click Replace File. Someone had already imported this. I'll go ahead and just re-import it just to show the steps. That someone was probably me when I was testing out this workshop earlier. Now that the data has been imported, I'll click the Available tab, and we'll just look at it real quick. If I click the HMEQ data table, we see after it loads for a second, it gives us some information about the columns in the data. There's a column BAD, which stands for Binary Applicant Default. This is banking data, so information about banking customers, historical information. Binary Applicant Default is whether or not these customers defaulted on a home equity loan. The HMEQ stands for home equity data. And of course, the rest of the inputs then, loan, mort due, value, these are all inputs about the account information. So the value of the loan, the mortgage value on the house where they're taking equity out of, the reason for their loan, their job, their years on job, various inputs that will be used to try and predict whether or not they default on this loan. I'll click OK, and I'll click Save. The very first thing we do when we've created a project is set some metadata for our predictive modeling task. So I mentioned that we have this target BAD, binary applicant default. The very first thing we'll need to do is tell the software that we want to use this as a target for all of our predictive modeling in the subsequent modeling that we'll do in Model Studio. So I'll select bad, and of course it immediately warns us that we do have to assign a target before we do anything. I'll change bad from input to target, and I won't make any more metadata changes. We'll use the rest of the columns in this data table as inputs for our predictive modeling algorithms. I'll click Pipelines to go to the Pipelines tab to build a machine learning pipeline. We start with data. Some of our values in our data are missing, which I happen to just know because I'm familiar with the data set. We might have wanted to explore it to double check that. I'm going to right click on data, add child node, data mining preprocessing, imputation. I want to impute missing values in the original data set so that when we build our predictive models, we don't have any missing values that we're feeding them. By default, we're replacing class inputs, that's categorical columns, with the count method, which is basically the mode, so whichever level is most common. And we're replacing missing values from interval columns, so numeric columns, with the mean of the column, the mean of the non-missing values. I'll add a predictive model here. I'll right-click on imputation, add child node, supervised learning, gradient boosting, and I'll leave the gradient boosting on the default settings, but I'll go ahead and also add a neural network model. So I'll right-click on imputation, add child node, supervised learning, neural network. We've got two predictive models built by SAS, a gradient boosting model and a neural network model. We'll also add in an open source model. So I'll right-click on imputation, add child node. This time it's miscellaneous, and we'll add an open source code node. Before I do anything, I'm just going to right-click on the open source code node and rename it just so I know what it is. I'm going to be building a Python forest, so I'll name it Python forest. So I'm going to build a forest model using scikit-learn and Python in this node. From the node, I could right-click and select Open, or I'll just click over here and click Open Code Editor. There's some notes about essentially building Python code in here, but I'm actually just going to copy and paste some code that I have in a file. So I'll go to my desktop, I'll open my Python forest code.txt file. This is just some code that I prepared in advance. I'll copy all of the code. I'll go in here and paste it over. It actually wants me to use Control B to paste. I'll paste using Control B. Real quick, just before we run this code, let's look over it real quick. We're going to import the ensemble model from scikit-learn. DM input is a variable that SAS automatically renders, which is the input variable set in metadata that we already chose. So this is a Python variable SAS defines for us. And we're going to add the partition to the inputs and call all of these inputs full X, which we're going to feed to scikit-learn. We need to dummy encode our categorical variables. SAS does this automatically. Python requires we do it manually here. We want to split our data into training data. That's essentially looking at that partition variable and selecting out the training and validation data. For now, we just need the training data. We also need the targets for the training data. In SAS, we just sort of have the entire data table, training inputs and targets. Scikit-learn expects them separate. We have some parameters that we set for the random forest model. And then we build the model, naming it something DM model, which is actually a variable that's saved into SAS. We use the fit method on this model. This is scikit-learn code to actually fit using our inputs and our target for the training data. When we do this, it renders variable importance tables in the form of data frames that we can consume. So we get variable name and variable importance from scikit-learn. We're going to write this out as a comma-separated value, a CSV file, and we're going to put it in this location, dm_node_dir, which is a directory created by Model Studio, essentially. So this is code that's going to be run on the server. It's run on a single machine in Python, but the results are going to be saved to the server in this particular location. And that means that Model Studio will be able to consume these results and display them to us later. At the very end of the code, we score the data, and we output the scored data as this object dm_scored_df, which is a data frame of scored data, which will be consumed by SAS for generating assessments. So here we're actually scoring the validation data, or actually the full data set, not just the training data, the training and the validation data. And the scored columns are p-bad 0 for the probability of binary applicant default being 0, and pbad1 for the probability of binary applicant default being 1. We'll save the code. We'll close our results. Or not our results, we'll close the code editor here. I'm going to right-click on the Python forest. This is a predictive model, so I'll select Move to Supervised Learning. When we moved it to Supervised Learning, we notice it goes from orange or yellow to purple, telling us that this is, in fact, a predictive model. We have the option to generate a sample of the data. Our data set is only 5,950, I believe, rows, which means that if we sample 10,000 observations, we'll get the full data set. So I'm in fact, just going to turn sampling method to none. Normally, we might want to use a data sample because SAS Viya is a distributed computing environment and Python runs on a single machine. So we'd have to kick back all of the data to a single machine. This data set just isn't very large. We want it to run quickly and easily for this demonstration. So we don't really need to do a sample here. I'm also going to uncheck include SAS formats because we do not want to include the SAS formats when we send the code over to Python. It doesn't need them and might confuse it a little bit. All right. Now that we have our sort of full pipeline created, we can run the pipeline. Now that our pipeline's finished running, we can right-click the Python forest model and select results. These results include some results from Python, so we see this Python output down here on the bottom left, which is when we printed the model, it's a random forest classifier, and it lists all the settings for the model. We also see the raw Python code. I just like to point this out because I think this is neat. We see here below at the bottom, this is the code that I pasted in to the code editor. So this is the Python code I wrote to create the model. At the top, this is Python code that SAS wrote to create these variables that I talked about. So things like the node directory, which is a location where the files in the node might live for them to be surfaced. We'll see one of those files in just a sec. Some of the categorical and interval inputs, all of the inputs, targets. It also has importing the pandas module, as well as loading the data into a pandas data frame. So various things that SAS does for you automatically in the Python code node. This rpt underscore var im underscore csv is the variable importance table that we wrote out as a CSV file from Python. When we saved it into that node dir location, that directory for this Python node, this Model Studio node, it allows us to surface this table here in the results tab. So we see variable importance for some of our imputed variables. Notice that some of these are categorical variables. So they have many levels. I'll go over to assessment. These assessments are created automatically from the scored data frame that Python gave to SAS. So we get cumulative lift plots for training, validation, and test data. We also get ROC charts for training, validation, and test data. So these ROC plots were created from the scored data. This is done by SAS, although the scored data was generated from the Python model that we created. I'll close the results here, and I'll go to the model comparison node, right-click, select results. We see the SAS gradient boosting model ends up being the champion model based on the KS-Uden statistic, although it also has the lowest misclassification rate. We can see more fit statistics here. When I go to full screen, I can look at average squared error. The SAS gradient boosting model definitely does the best there as well. Evidently, this SAS gradient boosting model will be our champion model. If I go over to assessment, I can compare all of these models. So I could look at ROC for, let's say, one partition. I'll choose the validation partition. I could compare the three models on validation data. It looks like the Python forest and the neural network do fairly similar, and the gradient boosting model is much stronger. I'll close the results of the model comparison node and go over to pipeline comparison. We really only have one pipeline in our Model Studio project here, but pipeline comparison is the way that we're going to get access to the deployment tools in Model Studio. So we see our gradient boosting model is selected as our champion model for pipeline 1. If we had other pipelines, we might see other models here. Here we just see the results of the gradient boosting model. We'll go ahead and register this model as our champion model into Model Manager. So I'll click these three dots, the snowman menu on the right, and I will select Register Models. Once the model is registered successfully, we can go into Model Manager to look at the model and the model properties. So I'll go up to the left, select the Show Applications menu. I'll choose Manage Models. This takes us to server, the SAS Viya server / SAS Model Manager. Model Manager is the application we'll be using to manage our models. Here we see a list of models. Here's the gradient boosting model that I just registered. Here's a couple of other models. They were registered by the student account, but they were registered by other instructors associated with other courses. You'll notice some of these are text analytics models that have been registered. I'll click over here on the left. I'll click this projects option. I would never have guessed this was projects just from the picture. So I usually like to click these arrows at the bottom to get a list of options here. So I see projects. I'll click on projects, and I'll select the Model Manager Workshop project. Here we have the gradient boosting model. If I look at variables here, we have variables registered into this model project. Here's the input variables, all of the inputs needed. The output variable is the probability. EM event probability is the probability of default that is generated by this gradient boosting model. We'll go ahead and set some project properties here. We could add a useful description to tell people what's going on. It's automatically identified that this is a classification project, but we should give it the target variable, binary applicant default, or bad. The target event value is 1. The target values are 1 for the event and 0 for the non-event. The target level is binary, so it's a binary target. And the output event probability variable, and this is important, this is EM event probability. The reason I mention this is important is later on we'll see if we don't have SAS models, this might be named something different. So this is the default name for SAS models, but other models might have a different output event probability variable. I'll select EM event probability, and I'll click Save to save the model properties. Now that we have the model properties, we could do things like score tests for our model, but before we do that, let's register in one more model. We're going to register in an open source model from R code. Let's look at some R code real quick. So I'm going to go into my course folder. I'll open up this R logistic regression code.txt. I'll go through this fairly quickly. Let me make this a little bit bigger. We start in R by imputing the data. We load our CSV file in, so here's our raw data file. We're going to find missing values for our interval and nominal variables, and then we're going to impute our interval and nominal variables. We're going to partition the data in R. We're going to build a logistic regression model. So this is all data preparation up above. Here we're actually building the model, a general linear model, so it's just a logistic regression model. The target is bad, and we're going to use all of our input variables to predict it. And finally, the important step at the end here is we're going to load the PMML library and save our model as a PMML model. That's predictive modeling markup language. It's basically just a standard for model formats. We'll save this XML file in that format, and we will load that into Model Manager. In addition to saving the XML file, which really is all we need to load our model into Model Manager, we'll also generate some fit statistics and some information that we will find useful in Model Manager in the form of JSON files. So here we're just writing some JSON files. We load this JSON library. We're writing this dm-cas fitstat SAS JSON file. We're essentially modifying it. This was a template, and we're filling out this template with the fit statistics values from this logistic regression model. We fill it out with things like average squared error, C statistic. We do test data, validation data, and training data. We also create a JSON file for the ROC curve. So again, we're just writing information that the model generated out into a JSON so Model Manager can consume it. We're going to generate predictions for our model, then generate the ROC information. We have to do this manually in R because essentially R is the source of the model. That's how we're going to actually generate the scores. So we generate sensitivity and specificity, use that to construct the ROC curve, and export it as a JSON file. I will exit this. We've already run this code, so we have, and I'll just point this out, we have the XML file that was generated, as well as some of the JSON files, the fit statistic JSON files. Here's the 2 that we just created. I will go back to Model Manager, and I will click Import. Lost my mouse. I'll import a model, Select one file at a time to import model contents. I'll select the XML file that I created. So we'll look at R logistic regression model.xml. Click import. I'll just name it R logistic regression model. That's a fairly descriptive name. I'll click the box next to the model, and I'll register this as a challenger model. So this model was the gradient boosting model defaulted to being the champion model, and that's that role right there. So we see that's the champion model role. We'll register this as a challenger model. I set as challenger. When I set the model as a challenger model, it tells me we expect this output EM event probability. That's what the other models were generating. What's the output from this model? Well, this is the R model, and it outputs the target, the prediction for the target as predicted underscore the target name. So in this case, it's predicted underscore bad. I'll click save. This registers this model as a challenger model. I'll go over to scoring, and I want to do a test score of this model to make sure that it works correctly. So I'll create a new test. I'll just name it test 1. When I choose the model, I'll choose the R logistic regression model. For my input table, I'll just score the HMEQ table. If I had some sort of score data, I could test it on that. I'll just use the same data set. I'm really testing the mechanics of scoring just to make sure that the system has loaded the model correctly. Click OK. I can click Save to save the model, but I can also just click Run to save and run the model. By default, it'll output the scored data to the public CAS library. I'll click Run to run the score test. The score test is completed successfully. We could click the results and look at the results. I just real quick want to see that there is actually a column of scored data. So I'll click Output. This allows me to select the columns I want to look at. Predicted bad is the column that I'm interested in. It is visible. Let me just scroll down. Grab this window, scroll all the way to the right. Here we get generation predicted bad for some of our values. Yes, we were missing predictions on some of the columns that are missing values, and that's because when we actually scored the data, it needs the input. So we didn't impute any missing values before we generated the scores. So this is a lesson for us that when we actually score our production data, we want to make sure to score it by imputing the missing values first so that it knows how to score it. I'll close these results. I'll go back to models. I'll click on the R logistic regression model to open it up. When I've opened the model, we see a list of files associated with it. Here's the score code, the XML file we uploaded, and an XML of inputs and outputs. These are just simple XMLs listing inputs and metadata. We're missing some fit statistics and the ROC curve that we created in JSON files. So I'll click Add. I'll select a few files to add. I will add dmcasfitstat.json and then hold Control and make sure to add dmcas underscore roc.json as well. I'll click OK. I'll click Add. And now we've got more files loaded into Model Manager that give us information about our model performance when we built the model. Adding these also allows us to do some model comparisons between models in our project. So I'll close this R logistic regression model to go back to the project. Oh, it actually takes me back to the Models tab. I'm going to go back to the project. Here's our Model Manager workshop. I'll click Gradient Boosting and R logistic regression model. When I've selected them both, this Compare option is available. So I'll click Compare. This generates a side-by-side comparison of some model information. So we see they have the same inputs. Oh, I could look at it a little longer, but they definitely have the same inputs. The output variables are going to be different because the SAS model generates all these imputed variables, whereas the R logistic regression model just generates this predicted bad. It does the actual imputation in place is basically the way I think about it. So SAS generates new variables, whereas R imputes over the existing variables when we actually trained the model. We also see some fit statistics. We have fit statistics for training data, validation data, and test data. The values from the SAS gradient boosting model get loaded automatically from Model Studio. these data values came from the JSON file that I just uploaded. And we see these plots, lift, captured response, and then ROC, or cumulative captured response. And then down here we see ROC. I wanted to highlight, we see an ROC plot for the R logistic regression model because we loaded that ROC JSON file. So we loaded that information from R into Model Manager. We don't see these lift charts because we chose not to load that data. We could have easily done that, just would have been a little bit more work. I can click Show Differences to see the differences between the model. Of course, most of the fit statistics and the plots will be different. So I think that's more useful when you look at input and output variables. I'll close these results. These are our two models. If we have built our models and we're satisfied, we can choose one as a champion and one as a challenger. But if we find our models aren't doing very well or we want to change them, we have some options for retraining our models. These retraining options essentially are for building a new model using all of the same settings if you've gotten new data. So in our next demonstration, we'll be looking at monitoring model performance over time to try and see if your model's been degrading. In this demonstration, we'll look at some performance data sets, so different data sets over time that we've collected to evaluate how our model performance might degrade as we move past the time when the model was created. So I'll go back to the top left, select the Show Applications menu. I'll click Manage Data to upload some new data sets. I'm going to upload my performance data sets. This takes us to SAS Data Explorer. This just allows me to upload some new data. I'll go to Import, Local Files, Local File, and I'll select HMEQ_1 through HMEQ_4. And I will click Open. I'll click Replace File because I might have imported them a little bit earlier, and I'll click Import All. Now that these files are imported, I'll go back to Model Manager. So I'm going to navigate back to Manage Models. This takes me right back to my Model Manager workshop. I'll click on Performance to create a new performance definition. These are performance reports which evaluate model performance on different performance data sets, which are data sets that you've collected over time. So of course, it's your responsibility as the modeler to have the right data. You feed it in here and it'll tell you how the model changes. When we create a new performance definition, we will use a library that contains tables with a specified prefix. I loaded these tables into the public CAS library. I may have forgotten to mention that, but that is the default. So I'll scroll down to public, select OK. And the prefix is HMEQ. So all of the data sets were HMEQ_1, HMEQ_2. That ordering, I guess, the numbers there matter, and the software is going to read them out and build performance reports based on these numbers data. We have some information about what those numberings are. Basically, it has to have a sequential number at first and then a time ID. So you'll see the data set was something like HMEQ_1_Q1, HMEQ_2_Q2, et cetera, et cetera. I'll name this performance test performance report. I will not include a description. It's often a best practice. We've selected the tables that we want. We're going to use the reference model, so we'll just use this champion model, the gradient boosting model. We want to evaluate it on the champion model. It defaults to the right input and output variables as well as the right properties. So we'll just go ahead and click Save here in our performance report. Now that I've created the definition, I have to run it. So I'll click Run to run the performance report definition. Now that the performance report has finished running, we can look at how some of the variables might be changing over time. So I'll look at the variable distribution for years on job. And we see that so these bins are just bins for different numeric values of this years on job. And we're looking at the different quarters. So we see as our years are changing, basically as our quarter is changing throughout the year, our data is changing dramatically. So we see the distribution of this years on job variable is dramatically different in these different data sets, which indicates potentially that we might need to retrain the model to score on newer data. Some of these other variables don't exhibit the same pattern. So if we look at things like CL age, this is pretty much unchanged. You only see one because all of the others are underneath it. So this variable hasn't been changed very much. So that's sort of how I read these plots, is we're looking for differences across these bins of different differences across these different colors for these different variables. We also have a deviation index, which sort of is illustrating the same thing, but we see most of our variables don't have very much deviation as we go from quarter one, quarter two, quarter three, quarter four, but our variable years on job, YOJ, deviate significantly as we go from quarter to quarter. I like to look at this lift chart. We see at quarter one, we have the best lift. Quarter two, our lift is going down a little bit more. Quarter three, we have lower lift. Quarter four, our lift is even lower. Basically, the way I read this is as we move further and further in time from where we trained our model, the time when we had the data that actually trained our model, we see that the lift is degrading because we're capturing less and less signal. There's new signals in the data that we're scoring that are not present in the training data that we use to build the model because things have changed over these quarters. We can see the same information in the form of the ROC curve. Quarter one has the best ROC curve, quarter two's next, quarter three and quarter four are a little bit weaker. We can look at model evaluation statistics like the Gini index or the KS statistic to see that both of these model performance statistics, bigger is better for these assessment statistics, they are degrading as we go from quarter one to quarter four. This tells us that we probably want to retrain the model. So I'll go up here to this button, click Actions, click Retrain. I'll retrain the model on the newest data. So rather than I could just set the project to say retraining is needed and let someone else be responsible for it. Since I'm sort of trying to demonstrate this for everyone, I'll be the one who takes responsibility for retraining. So I'll retrain now with a new data table. And I'm going to go ahead and browse and actually import the newest data table I have. So I'll go to Import, Local Files, Local File. We have this HMEQ_5_Q5. This is the newest data we just collected, perhaps let's say last quarter. So we want to retrain our model on this newest data that we have. I'll click Replace File, Import Item. Once it's been imported, I'll click OK, and I'll send this to retrain the model. And we've triggered the model for retraining. I'll go back to the models. I'll go ahead and refresh here. Sorry, I had to refresh it real quick. It got a little bit confused because I asked for a little bit too much at once before refreshing it. We want to look at all versions. It's still doing the retrain. So we're waiting for version, here we go. So it just finished the retrain. Version 2 of the gradient boosting model has now shown up. And that was the model when I retrained it on the newer data. This is the newest model, so we want to actually deploy this model. So I'll select this model. There's an option here. I'll select Publish to publish to a scoring location. Currently on this virtual machine, we only have the ability to publish to MAS, Microanalytics Services. But there are other publishing destinations that you can have. And in our newest version of Model Manager, there's actually the option to publish to Docker containers, which is very exciting. So I'll click Publish. And when I publish, it will send this to this Microanalytics Services location. So I can call scoring basically via an API call to call data, any sort of data that I have against this model. And SAS Viya will generate the scores for that. I'll close these results and we'll look at the history. I'll go ahead and refresh this. So we can see what we've done. We created the project. We've done some editing. We set a couple of champion and challenger models. And at the very end of the day, we published to SAS Microanalytics Services, this location, MAS local. And incidentally, I'd just like to point this out. If I go back to models and I click on this model that I published, this gradient boosting model, it has this A-store file. It's this incomprehensible file. I always like to click here to show that it's an analytics store file. It's basically a binary file, and this is what is actually going to be doing the scoring. So when you generate scoring, you'll score against this file. Excellent. So those are our steps for deploying and managing models using SAS Model Manager. This gives you the ability to sort of manage version control and history of your models, as well as keeping track of everything that's been done and deploying them all in some central location. Thanks. To wrap up, I wanted to point out a few other deployment options. We registered our models into SAS Model Manager. We published it as an A-store file into SAS Microanalytics Services. We could have also registered our model and published it as data step score code, and we have a couple of different publishing locations. SAS Cloud Analytics Services is basically just publishing it into the SAS Viya server to score on the SAS Viya server where we trained the model. SAS Microanalytic Services is where we published our model. This is a more portable format where we can deploy it anywhere where SAS code can run. SAS Event Stream Processing allows us to publish our models directly into SAS Event Stream Processing, an engine for reading in and scoring streaming data as it comes in. So the microanalytic services and cloud analytic services are used for scoring data at rest, and SAS Event Stream Processing is used for scoring data on the move. We also have some other options if you're using other SAS tools. So I just wanted to point out another deployment pathway that is a little bit more complicated, so we don't illustrate it in this workshop, but I think it's interesting to think about. We generate a SAS model using DLPy, which is deep learning in Python using SAS Viya. So we're using Python code to build deep learning models in SAS Viya. Once we've built these deep learning models, for example, perhaps an image classification model, we convert them into the ONNX model format. So that's Open Neural Network Exchange. So we've converted this deep learning neural network into a standard format that's kind of, I think of it sort of similar to that PMML XML file that we generated for our R logistic regression model. And then we take that ONNX model and we can deploy it to devices, for example, like people's iPhones or Android. Now, depending upon the device you want to deploy it to, you might have to convert the model a little bit. So to sort of show a little bit more complicated this pathway, we deploy the DLPy model. We can automatically create this Open Neural Network Exchange XML file, basically. From there, we have to convert that XML file into something that, this is for an iOS application, something that the iOS engine can actually read. So CoreML is tools for machine learning on iOS developed by Apple. So we have to convert our open neural network model into something that our iOS can read, deploy it as an application. We have to write that application on iOS and then send that over to a device. And SAS has some demonstrations there. I can't really show it in the context of this workshop, but SAS has created some of these demonstrations, and customers can do this as well. This is, of course, much more complicated and is going to require a lot more work than sort of deploying a simple business application using all of the SAS tools, but there's a lot more flexibility if you want to do edge devices or deploy things to people's phones. Excellent, thanks.